So I have a breastplate here for valve that is used in a car. It's made of this brass alloy. So what we want to do is we want to see if we can make this, find a better performing material. It's a car, so obviously we want something that's lighter, and of course cost is also important. So the idea is that we can start by recognizing that how is this component loaded, what is important. When you know what is important, then you also know what you want to optimize. And in this case, we also have we can make this plate a bit thicker. And why does that matter? Well, imagine you had a material that was like a lot weaker. Let's say it had a yield strength that was like half of what you're currently using, but it was 10 times cheaper. So you could make a component that was a little bit thicker, and you would still have the good mechanical properties, but you'd be able to save a lot of money potentially. Okay. So what we will do here, where the database comes in, is that we have some constraints, some thermal constraints, and some constraints about the environment. So what we will do is we'll say we have a database of a lot of materials. Let's apply some filters and then remove all the things that we know, for instance, cannot do the temperatures it needs to do. And then what we've left in the end, we can use an index or a ratio saying ranking by this ratio, and then we can use this to find the best materials. So the idea is it's quite simple. We have a database, we remove, and then we rank the remaining materials, and then we use that to find something to see which candidates there could be. So I will just jump into the program and show you how we could do this. So just a bit of cleaning up firstly. So what I will do here is firstly I will just find the material we are currently using, and I'll set this as a reference point. So and the reason I'm setting as a reference point is just so we have something to compare against. Okay. So the first thing I will do is saying I have a database of over 3,000 materials. So let's apply some constraints here. So we have some constraints about the temperatures it has to be able to withstand. We also have some constraints about thermal expansion, naturally, as this can also lead to horrible product performance. Then we have it's a car, so obviously we have some constraints on salt water with all the snow going around in much of Europe now, and all the salt. Your car definitely needs to be able to withstand salt. And then obviously also something like organic solvents. So if we apply this, we can look here and at the list of results and see that we've narrowed this down from 3,000 materials below to 300 materials. So already by using this database, which you can apply filters to, we've removed a lot of materials that we know we don't have to consider. However, we have 300 materials left. So first of all, I'm going to make it a bit more simple yet. And that is that I also want to make sure that we're not end up with a material we cannot fabricate in a wrong way. So I will just put some constraints saying that it has to be able to be processed either by sheet forming or by injection molding. So by doing this, I've narrowed it down to 200, but 200 is still a lot of materials. So what we can do here, which is actually quite smart, is that we can plot the material properties. And this will make it a lot easier to see which materials will actually have a nice performance and which won't. Okay, so just stepping one back. So what we plotted here is the cost per unit of stiffness and the mass per unit of stiffness. So the idea is that by plotting by these units of stiffness, you can account for the situation where you can make a material a bit thicker, but then save a lot of money, for instance. However, what we see right now is something like aerated concrete and balsa, not materials we would commonly go for in a situation like this. So what we can do is we can apply the constraints, and that will remove all the wrap materials. We remove them, and then we basically have all the materials that we could consider left. And then we can see the ones that has the lowest cost per unit of stiffness and mass per unit of stiffness. That will be the ones that are worth considering. So I can just show a few, like a polymer, PPS. We have some stainless steels. We also have some brass alloys. For instance, here we have our reference material. I can just make it a little bit more clear. So this is the material we're currently using. And we can actually see here that we have some materials that has lower, that's actually a lower cost per unit of stiffness and mass per unit of stiffness. So what this actually means is that we've used this, and then we can see quickly, do a screening, and then we can use this to identify potential candidates. So if we jump back to what this means, then it means that we actually, if we switch to something like this PPS with glass fiber and mineral, you can actually see what we can do here is we can reduce the rate by 60%. We can reduce the raw material cost by 25%. We have to make the component 7 times thicker. In this case, it's the good story where we, by using this database, then removing all the candidates and then visualizing which materials is left based on some ranking criteria, then we can actually, with a little bit of work, get a good idea of which materials you could use.